Classes in Statistical Mechanics. Lectures by Professor George Phillies, based on his book, Elementary Lectures in Statistical Mechanics, Springer Verlag, 2000. And today, this lecture is Lecture 3, The One-Atom Ideal Gas. This course is the Special Topics Elementary Lectures in Statistical Mechanics, based on my own book. I'm Professor Phillies, and you can't see my students. They're hiding out of sight. Okay, so in our first two lectures, we discussed statistics. We discussed history a little bit. I introduced the ensemble concept. What I'm going to do today, first of all, is to go back to the beginning a bit. And the notion of going back to the beginning is, what do you have when you present a physical theory? And one piece of the answer is, well, you have the basic equations. And the basic equations are Maxwell's equations, or the Schrödinger equation, or F equals ma. And that's the explicit, those are the explicit pieces. Then there are implicit pieces. For example, in classical mechanics, there is the implicit piece that it's useful to talk about things like energy and point masses. In quantum mechanics, that's much more transparent. In quantum mechanics, an implicit assumption is the Copenhagen model, and the Copenhagen statement tells you what you do with the wave function now that you have found it. Finally, in putting together any physical theory, there are things that are neither explicit nor implicit. They're the exemplary problems you work, and by working problems you see what the theory actually did. The exemplary problems are important because they show you how to approach things. For example, if you were to do with a theory of the hydrogen atom using quantum mechanics, and if you were to assume that an electron was a uniform spherical shell of charge the size of a grapefruit, you could indeed calculate the hydrogen atom spectrum. And it would be a completely correct calculation, except for the minor detail that it would not resemble the hydrogen atom because your electrons are wrong. So we do all of these pieces, and eventually things come together. To discuss the statistical mechanics, what we did is to say, well, first we have the requirement that we have to be able to get a mechanical description of the system. If you can't do that, the theory can't be applied. If you think about things, when I said we can do a complete description of the system, there was something implicit that we eventually work around. That is, I said, we can, for example, list for each particle all of the coordinates and all of the momenta. And if the system has a whole lot of particles in it, the list gets extremely long. Suppose, however, the list of particles in the system, so to speak, was countably infinite, or just infinite, period. How would you then advance? Well, we'll get to that eventually. What I'm going to do today is to work through an example of how to apply statistical mechanics. It will be the simplest possible example. It's the one given in Chapter 4. But since I mentioned Chapter 4, I should mention there is Chapter 4 homework. And the Chapter 4 homework is problems 2, 3, 6, 8, and 9. They're due in a week.
2, 3, 6, 8, and 9?
Yes. My little note says that 4.2 is actually a difficult problem unless you see how to use the hint. And if you don't pull it off, you don't pull it off. If you see how to use the hint, it's a very easy problem. 4.3, in working 4.3, you're supposed to assume that you knew what equation 4.41 did. Okay? So that is the homework. It's right here. And now we will push ahead to Chapter 4. Chapter 4 also illustrates the superiority of the Gibbs model of statistical mechanics over the Boltzmann model. The Boltzmann model only works if the number of particles in the system is extremely large. The Gibbs model of statistical mechanics, and Gibbs demonstrates this at considerable length, well, for him anyhow, it's considerable length, in his book. Gibbs demonstrates that his model, his treatment of statistical mechanics, works equally well for large and small systems. So we are going to take the smallest gas system you can imagine. It's a box, and it contains one gas atom. Can't get smaller than that. The gas atom is a point. Now, if we had here is a representative gas atom. If the gas atom had extent and pretty colored structure, the gas atom would have the feature that you could store energy internally by flipping head over heels. Well, our gas atoms can't do that. Instead, our gas atom is like the one between the two fingers. It's a mathematical point. And to describe the gas atom, we need only 6 coordinates. Because the gas atom has a position. It's someplace in the room, x, y, z. And it's moving with some momentum, p sub x, p sub y, p sub z. Notice that I use momentum rather than velocity, and there are good reasons for doing that, which we'll touch on late in the course. We will eventually talk about the stability of the canonical ensemble. I'll say more about that in a bit. Okay, so we said there's 6 coordinates. The momentum components, px, py, pz, can be anything from plus infinity to minus infinity. The position coordinate you can handle in 2 ways. You can say, here is my trusty drinking cup. There's a lid on the top. The gas atom is in there someplace. And therefore, the allowed gas atom components, position coordinates, are the ones that put the gas atom someplace inside the system. The other thing you could, of course, say is the gas atom can be anywhere, but its potential energy is plus infinity unless it's inside the container. And if the potential energy is plus infinity, except when it's inside the container, well, if the statistical weight is exponential minus beta E, and E is infinity, let's think for a second, what is the statistical weight if the potential and energy is plus infinity?
0.
I hear a 0.
I'm going to go 0.
Yeah, e to the minus infinity is 0.
Mm-hmm.
Okay, so the gas atom has to be someplace inside. We have constrained the number of particles. There's 1. We have constrained the volume, and there is some temperature T. We're going to follow the route of saying the gas atom is constrained to be inside the container, because in that case the energy of the system is purely its kinetic energy. And we can write the kinetic energy, well, actually we do write the kinetic energy in terms of equation 4.1. It's p squared over 2m. Or we could write that in terms of components, but the kinetic energy is the entire energy. Okay, now we're going to set up and calculate the ensemble average of some property of the gas molecule. So in order to do that, it's an average, and the average has all of the same pieces it did last time. It's a sum over all the states of the system of the statistical weight of that state times the value of the property of that state, and it has to be normalized. An example of an ensemble average is equation 4.2. 4.2 at first sight is extremely imposing. So let's go over the 4.2 in a little piece. The integral signs, which cover about 2/3 of each line, are just the sum over all of the states. So there are integrals dx, dy, dz. because we are summing over all of the allowed positions. We now have a triple sum rather than a single sum, but it's just a sum over all of the positions. And the positions are all possible combinations of x, y, and z. I don't have to tell you the shape of the container. I just tell you that G, it's someplace inside the volume. And then, for a particle, the atom being at, say, this one point and no place else, here's the atom. Suppose the atom is right here. The atom is right here, but it's allowed to have any value of px, py, or pz that it wants. So there's a list of 3 numbers for the 3 momentum components. And for an atom at this position, that gives me another triple sum, which is the integral dpx, dpy, dpz. Are we comfortable with this?
Mm-hmm.
Okay, and the p's, px, py, pz, each go from plus infinity to minus infinity separately. So if I say, let's go back to our definition of the ensemble. An ensemble is a complete list of all states of the system and their statistical weight. Yes?
Why would we allow momentum? Oh, wait, no, that's. I think I just realized why you guys choose momentum over velocity. Speed limit. C.
That's correct. If you did this in special relativity, momentum works better than velocity does. Mm-hmm. And you would have to rewrite things. That's true. There is another deeper set of reasons, but you're absolutely right. Gibbs, of course, did this before special relativity was discovered. As far as he was concerned, an object could travel as fast as it wanted to. Mm-hmm. Now, having said that, that means a single element of the ensemble is specified by a list of 6 numbers for a point atom here. But the full list of elements of the ensemble is 6-fold infinite, continuously infinite on all 6 axes. Okay, so the integral signs are the sum over all the states of the system. Then we have the statistical weight. And the statistical weight is the right end of each line. It's constant c times exponential minus beta, and a symbol which I write h, which is the energy of the system, which one of you will recognize as the Hamiltonian. Hamiltonian energy of the system. There are cases where the Hamiltonian is not the energy of the system. They do not come up in this course. Mm-hmm. There are no non-holonomic constraints or anything. It's just the energy. Mm-hmm. Okay, so there's the statistical weight, and Cx minus beta h is simply what we called Wj. Finally, there's the thing we are averaging, and in equation 4.2, that's A. And I don't tell you what A is, except that it's some function of R and P. It's a mechanical variable. It's a variable which for each state I can calculate by knowing the position and momentum in that state. The denominator of equation 4.2 is the partition function. And I write out the partition function separately as equation 4.3. Equation 4.3 is nothing new other than the symbol Q. Equation 4.3 is just the statement that the denominator has a symbol for it, and since it takes a piece to write out, we'll write it out separately. Okay, so now we have this integral. Let's suppose we want, because we do, to evaluate equation 4.3, the partition function. We have to evaluate the integral in 4.3, which is a 6-fold integral. Before you got to this course, had either of you ever seen anything larger than a volume integral?
I think for demonstration purposes in Calc 4 we did a 5-dimensional integral. But
Oh, okay. Well, we're by and by in another chapter or two, we're going to have Avogadro number of dimensions in the integral, and we do not write this out explicitly because the poor publisher would have gone broke typesetting it or printing it anyhow. But to do these integrals, which get quite tedious, there are some tricks, which are equations 4 through 6. And equations 4 through 6 are all standard calculus steps, which undoubtedly you did see. And the first is to say that the exponential of the sum is the product rather of the two exponentials. The second says that if I have an two-dimensional integral dx dy, of a function of x times a function of y, I can split it into two single integrals. Now, implicit in that is the statement that the limits on the integral are constants or something, but in general you can do that separation as long as there's nothing funny that I didn't write out. And that's a standard calculus trick too. The third is that the integral of a sum is the sum of the integrals. So far, so good? When with those tricks, we will now do the actual integral. The first point, which is equation 4.7, is that the energy of the system can be written as the sum, it's in 4.1, of px squared over 2m plus py squared over 2m plus pz squared over 2m. And once I have the exponential of a sum, what do you see me doing?
Split it up.
Yes? Split the sum into three terms. And so I now take the three terms in 4.7, the exponentials of px, py, and pz, stick it into 4.3, and I notice something. My functions, there's a function of px times a function of py times a function of pz, so I can use equation 4.5 to split up the partition function. And in particular, there's a constant c in the statistical weight, and it just rolls out in front and sits there and does nothing. It will continue to do nothing until we get to quantum mechanics. Then there's an integral dx dy dz, but nothing in the integral is a function of x, y, or z. So I can take those three integrals and separate them out and put them to one side, and everything else can be integrated separately. And what is integral dx dy dz over the volume of the system? That's the definition of volume, isn't it? And then I have an integral dpx e to the minus beta px squared over 2m. I'm looking at equation 4.8. I have three of those terms. Those terms have a feature. Except for the label, the subscript x, y, z, what are they?
The same.
The same?
Mm-hmm.
Yes. And the integral can be factored into three separate integrals. We are going to chug ahead, actually fairly quickly, through about chapter 12, lecture 12. And we are going to be talking about what are called separable systems. What is meant by a separable system? A separable system is a system in which we have the energy of the whole system. We can break the energy into a series of terms. Each term involves only one or two of the variables, and all of the rest of the energy does not involve those one or two variables. Trivial example, except it's actually a very hard example, of a non-separable system. Suppose I have a box, and for no rational reason, no one would ever do this, I have filled the box with a plasma. And it's full of charged particles of different signs. Each charged particle interacts with all of the other charged particles. So if there are n charged particles, there are n times n minus 1. You're allowed to put in a 1/2, but it doesn't really do anything. Terms, and everything interacts with everything else. This makes it slightly more difficult than our problem today. Just a bit. But no one would ever have any reason for doing this. And as one of you can tell, I am deliberately saying this because one of the people in earshot is going to plasma physics. Okay, now that I have had my moment of fun, let us push back. And we will go on to equation 4.9. You remember I said there are three momentum integrals, and they're all the same.
Mm-hmm.
And in 4.9, I tell you what the value of that integral is. Doing it has already been left as an exercise for the student. It was homework problem 4.2. I will give you a hint. If you actually try to do the integral directly by brute force, you have to be quite clever. There is a trick which makes it trivial, and the trick is to square things, change coordinates, and take the square root. Then it gets easy. Okay, well, we've done all of the parts of the integral. So what I have told you is if you take 4.3, which is the partition function of the one-atom ideal gas, and you evaluate all the parts, which is what we did on page 41, you get the bottom line of page 41, which is equation 4.10. It is the partition function of a one-atom ideal gas. And now we shove ahead, and we've got the partition function. Now we'd like to take the average of something. Remember, we were looking originally at equation 4.2, which is the average of some unspecified quantity A. Now we'd like to actually compute that average. In order to compute it, I've got to choose a function A. So, of course, you could choose the function A to be 1, and then the numerator and the denominator are the same. This is very interesting. One thing you could choose is to choose A to be x, or z, the height of the atom in the box. And you can calculate on the average the atom is in the middle of the box. Well, that isn't quite true. It's just it's 50% time below the middle, 50% of the time above the middle, and on the average puts it at the middle. But the thing we're going to choose for A is the kinetic energy of the one atom, p squared over 2m. And so if we skip ahead to page 42 and equation 4.11, I have written down the average value of p squared over 2m. The next step is to do the average. Now, those rules I gave you a little earlier, the three basic calculus rules, let you do this. There's nothing clever about it. The usual complication, if I just threw this at you and told you this is a homework problem, is that you would become slightly absent-minded and you would lose terms. So the first thing we do is to say, equation 4.12, I can split p squared over 2m into its three pieces. And when I do that and stick 4.12 into 4.11, I have an average, 6 integral signs, a statistical weight, over px squared over 2m plus py squared over 2m plus pz squared over 2m. That's 4.12. The next thing I do is to say the integral of the sum is the sum of the integrals. Yes?
Mm-hmm.
And now you have to be alert and awake and realize that when you apply those rules, all the integrals are still there. And so when you apply those rules, you will have now three terms. For example, the term in 4.13, which is the average over of px squared over 2m, but all 6 integrals are still there. And there is an absent-minded tendency to shed integrals and then get really strange results. I mean, really strange results, things that don't have any dimensional merit. Okay, so we split equation 4.11 into 3 terms, and I've only put down one of them as equation 4.13. And equation 4.13, I have also said integral dx dy f of x g of y, I can split. And I did that split when I evaluated the partition function. And here I've done it again. So for example, the integral dx dy dz, there's nothing out there beyond the integral sign to their right that is a function of x, y, or z. So I can do those three integrals all by themselves, and nothing else matters. Good so far? However, when I do the momentum integrals relative to the partition function, I have one little complication, namely, there is a px squared over 2m, or the equivalent, py squared over 2m, or whatever, which is in one of the integrals. And in 4.13, if you look at the first line of equation 4.13, the momentum integral, you see the px squared over 2m just sitting there. There are two more terms, and one has a py squared and the other has a pz squared in it. Okay, now we have to actually do the integrals. Now the volume integral we did before. The two integrals on the second line we did before. And how do you do the first momentum integral? It's homework problem 4.3. So you're going to work that one yourself, and I'm just going to tell you the answer. And the answer is that it is this factor 2 pi m kt to the 1/2 multiplied by a kt over 2. The regular integral is the thing in the square root. The integral with the extra p squared over 2m in it picks up a kt over 2. And therefore, 4.13 becomes equation 4.14. This is one of these steps where you're doing the math, and it is worthwhile for you to work it out by hand yourself. And you just do all the substitutions, and it drops out. There's nothing, again, nothing clever about it. Okay, well, the thing in 4.13 is the numerator of the ensemble average. The denominator of the same average is the partition function. And therefore, if you do the division, you're dividing 4.13 by the partition function, which is 4.10 on the previous page, and everything cancels. You see 4.10 on CV, open parenthesis, 2 pi m kt to the 3/2. Well, everything 4.10 divides into 4.13, and almost everything cancels, and you end up with a solitary kt over 2. So far, so good?
Mm-hmm.
Now you might wonder, if everything canceled, couldn't I have found the cancellations without evaluating everything? It's another homework problem. You write it out, and if you look carefully, you notice there's an integrator in the numerator over something and some object. There's an exactly identical integral in the denominator, and because the two are exactly identical, you can just cancel them without figuring out what they were. All right, well, that was the px squared over 2m term. You remember, however, if you go back to equation 4.12, the energy has 3 of these terms. Far so good? And therefore, you have to do this whole thing 3 times to find the average energy of one particle. You may reasonably suspect that when we get to all the atoms in the room, you want some alternative to actually doing the same thing. Avogadro's number of times. This would be tedious, to put it mildly. And therefore, there's some common sense summation sign things, but you end up with the average energy of our one gas molecule. Here is our 1-point gas molecule. It's in a room of some volume V, and its energy is 3/2 kT. Okay, well, now we can make several other comments on this. First of all, there is something called the specific heat, which is how the energy of the system changes with temperature. We are about as close as we get to thermodynamics. The specific heat is partial of E with respect to T. In this case, the specific heat is temperature independent, namely the energy is linear in temperature. And if I take d dt of equation 14, or equation 15, I find from equation 15 that the specific heat is 3/2 times Boltzmann's constant. The other thing, which we will come back to, equation 4.14, I say the average value of x squared over 2m, x is a coordinate, is kt over 2. That result is not an accident. It is called the equipartition theorem. And the equipartition theorem is a very general result. It's in a later chapter. But you've just seen the first example of the equipartition theorem sailing by you. Okay, that was the mean energy. We can compute something else. This is on the next page. And on the next page, we are going to compute the mean square energy. And so the energy squared is px squared plus py squared plus pz squared over 2m squared. So far, so good? Now, having said that's the mean square energy, if I want to calculate the mean square energy, I take equation 4.16, which is the thing being averaged, and stick it back into equation 4.2, the how we do an average. Sounds harmless, doesn't it? But if you think, 4.16 is the square of a trinomial, so it contains 9 terms. It contains 3 terms which are px to the 4 over 4m squared, and it contains 6 terms which are px squared py squared over 4m squared. 9 terms is a lot, isn't it?
Mm-hmm.
You'd love to do them all individually, wouldn't you? I see a lack of enthusiasm here. So we try to be a little thoughtful. The first thought, which we actually saw on the previous page, is that once we'd done px squared over 2m averaged, I didn't do the other 2 terms. I just said, gee, the other 2 terms are exactly the same, except I changed the indices. Everyone notice all I do is to do the other 2 terms is to change the indices, this x, y, or z subscript. Well, I can do that here, too. I can do that in section 4.3, the mean square energy. However, when I do that here, I discover there are 2 different terms.
Mm-hmm.
There are terms that look like px to the 4th over 4m squared.
It's the square terms and the cross terms.
Correct. They're square terms and they're cross terms. And there are 3 square terms.
And 6 cross.
You got it right. There are 6 cross terms. You have to speak up a bit more for the mic to catch you. Okay, so we can actually do those. And let's suppose we want to do them. Well, the cross terms we've almost done, except now it's like term 4.13, except now there are going to be a px squared over 2m in 2 of these. And now you get to turn the crank for yourself, which you should do. And when you do that, you discover you get kt over 2 squared. You get 6 of them.
Mm-hmm.
And there's also a term which has p to the 4 over 4m squared in it, like px to the 4th over 4m squared. And you can do that using the same method that got you equation 4.14. There is a method for getting that equation, and It gives you 418. That's another homework problem. It's not a very, that's a very easy calculation once you see. I mean, that's a really easy calculation, but you have to see how to do it. And now we put everything together and we get equation 4.20, which is the average of the square of the energy, which is 15/4 kT squared. So far, so good?
Mm-hmm.
Oh yes, notice that the mean of the square of the energy is not the square of the mean energy. The mean of the square of the energy is 15/4 kT squared. That's equation 4.20. The energy average squared is only 9/4.
Mm-hmm.
Okay. And I have now done an example of taking an ensemble average. There are now several different things we can do. One is to talk about the Maxwell-Boltzmann distribution. The Maxwell-Boltzmann distribution is sort of like e to the minus beta p squared over 2m, except instead of doing things for the momentum, we do them for the velocity. Well, suppose you took an equation like 4.11 and you replaced the momentum with the velocity, okay? Well, that would mean that in the exponential, the statistical weight is e to the minus beta m squared v squared instead of p squared over 2. That part's simple. The other thing is we have an integral dpx. Yes? Well, p is mv in Cartesian coordinates, and therefore dpx is m dvx. And since the thing goes from plus infinity to minus infinity, it doesn't matter in detail how it does so. That is, dpx goes from plus infinity to minus infinity when I change coordinates from p sub x to v sub x in classical mechanics. G, the integral still goes from plus infinity to minus infinity, doesn't it? So far, so good.
Would it go from plus c to minus c if you're just talking about velocity, or are we still going with
We're in
thought?
pure classical
Okay.
mechanics, no special relativity. If you switch into special relativity, life would indeed become more interesting, and the energy wouldn't be p squared over 2m anymore either.
Okay.
But we aren't going to do that. So we have a Maxwell-Boltzmann distribution, and if you can sort things out for the momentum, and you can sort things out for the energy, and you can read that part for yourself. We only have a certain number of lectures to get to the back part of the book. I am, however, going to talk about something which is fundamental and is important, and where your intuition will throw you off, and this is page 45. The issue is as follows. Let us go back to the definition of an ensemble. What is an ensemble?
It's a collection of particles in all of the
States possible.
yeah,
It's a complete, non-repeating collection of all possible states.
of the system.
And their statistical weights.
Yep.
Yes.
However, the ensemble is a complete list of every possible state.
Mm-hmm.
We just did an ensemble average, and it's very clear that the ensemble average really is a complete list. That is, that integral sign generates every single state of the system, the six-dimensional integral. It doesn't just generate some random collection sample. The ensemble averaging, the dx, dy, dz, etc., actually generates every single state without exception. And because of the way integrals work, each state is generated only once.
Mm-hmm.
So far, so good.
Mm-hmm.
Now we come to the notion, which you sometimes hear, that there are equilibrium states of the system and non-equilibrium states of the system. And so we have a system that is in equilibrium, or we have a system that is out of equilibrium. But I just told you what the equilibrium, or you told me, the equilibrium ensemble is a list of all states. So when we did this equilibrium average to find the equilibrium average energy, we actually went over every single state, not just a few of them. That means there's no room left for non-equilibrium states because all states are included in the equilibrium average. They're not all equally important because of the exponential minus beta E. I mean, the state in which our gas molecule here is traveling 0.999999 C, that has a lot of kinetic energy. And that state has a very low exponential weight because of the statistical weight. But it is an equilibrium state of the system. Okay, well, if all states are included in the equilibrium average, what did we actually mean when we said we are looking at a non-equilibrium state? And suppose we came in and you observed that the gas molecules in the room were so arranged that all of the oxygen atoms were on my side of the room and all of the nitrogen atoms were on your side of the room, and you had the sense to hold your breath, without which you would die very, very rapidly. Okay, if we actually see this, we do not suspect that the atoms or molecules were bouncing around random and sorted themselves out, as I described it. Instead, you can be extremely confident that hiding someplace are hidden vents and oxygen tanks and nitrogen tanks, and if you see a state like this, it must have been produced artificially because the likelihood that you would see it naturally is too low to be worried about. It's like seeing someone holding a bucket that had been full of little D&D dice, and they'd rolled the little dice, and all 1,000 dice are visibly on the floor showing sixes. Well, it could be they all showed sixes because 10,000 dice were all rolled and all of them came up 6, even though they're honest dice. But you're fairly sure that's not what happened. Even if your professor did once collect on a bet that he could toss a nickel and gave the other party heads and tails, I got edges. The other fellow was quite alarmed. In any event, when we say non-equilibrium, we say we think we are looking at states which we assume were produced by artificial intervention because we just can't believe it would happen while we were sitting there. It would be as absurd as a large election with millions of voters being decided by a few thousand. Never mind. Well, in any event, that is the actual distinction between equilibrium and non-equilibrium. If you see a state that we call non-equilibrium, we intuitively assume it's created by deceitful interventions of unnatural causes, as regularly seen in those newspapers you see in the supermarkets. Now, there's another piece that is related to this, which is sometimes called the arrow of time. What is the arrow of time issue? Well, we have laws of motion that describe particle motion. We have F equals ma. We have Maxwell's equations. We have the Schrodinger equation. We have the general relativity field equations. All of these equations have the feature that they have time reversal symmetry. That is, if we turn the universe around and so that everything is running backwards, exactly, we will see everything run backwards, and there is no violation of any law of nature. The microscopic equations are supposed to be time reversible. There is a technical issue here with the weak interaction and CPT invariance. We're going to ignore that one. However, we have the impression that if I show you a motion picture of something, like I drop ink into a glass and it gradually spreads out and becomes uniform, we can tell which direction is the forward direction on the motion picture. Yep. And there seems to be a contradiction here. I'm going to emphasize seems. And there is a whole huge school of physics called non-equilibrium thermodynamics, where people try to explain how you can get time irreversibility. The egg may break apart if you drop it, but it will never reassemble itself into an intact egg. How you can get time irreversibility out of reversible laws of nature. Yes? You see, you could imagine there was a problem here. And the actual answer is not at all, there's some trick that makes things irreversible. Now, working on this problem, trying to cause reversible equations to give non-reversible effects, even though it's obviously impossible, is very useful. For example, this is how Planck discovered, or rather created without realizing entirely what he was doing, quantization of electromagnetic waves. Namely, he had the idea that if you had a mechanical system and it interacted with electromagnetic waves in a metal box, you would have irreversibility. Maxwell's equations, as written at the time and traditionally applied at that time, a century ago, did not brilliantly display the fact they were time reversible, and if you hadn't thought extensively about it, it might have been a little less obvious that this clearly wasn't going to work. Planck did figure that out after a bit, but he thought it was an interesting experiment. Okay, so what is going on? Well, the answer is we have the states we would call the equilibrium states, which are the ones we expect to see. And if we sit around and wait, yes, sometimes the atom will be going faster, sometimes it will be going slower if it's in equilibrium with walls at some temperature. But we expect if we see the egg and it falls and spreads apart, we expect it's doing this. It's not the atoms of this mess on the floor all run in exactly the right direction and the egg assembles. Okay? And what this leads to is the actual explanation of time irreversibility, namely that any so-called irreversible process is equally impossible in both directions. That is, if we are in an equilibrium system, the egg spends most of its time down like this. And the only way you could have seen the intact egg up here in an equilibrium system is if you had first seen the egg assemble itself and jump up in the air. Yes? Well, it doesn't happen very often. In fact, it happens almost not at all. And therefore, you will almost never see the egg fall out of the sky and splatter on the ground, because that is an incredibly rare event, because before you could get the egg up there, it would have had to assemble. And therefore, the things that we call irreversible processes are equally irreversible in both directions. The process you call naturally the arrow of time is exceedingly unlikely to happen because you have to get to the starting point before you can move from the starting point to the conclusion. Do you see what I'm saying about the perspective you have just been given on irreversible statistical mechanics and irreversible processes is not the same as the one you will get in most courses, where all sorts of strange things happen, and you will perhaps be given something called the Boltzmann H theorem, which we now understand the core assumption is mistaken, is the politest way to put it. But the essential answer is there aren't really irreversible processes. There are just processes where you've somehow created the starting point by external manipulation, and if you just had a sealed system, you'd never get it to happen in either direction. Well, not quite never, but very, very nearly. Okay? Okay, that's irreversible processes. I have 2 minutes, and in 2 minutes I'm going to point out section 4.5 on reduced distribution functions. I am not going to work through the whole thing, but I am going to point out equations 4.26 through 4.29. And the notion is as follows. Suppose we have an ensemble average. That's what I've written in 4.26. And suppose the statistical weight is written as a function of 3 of its variables, n, l, and m. So we have a sum over all states, which is a sum of everything that n, l, and m can do. The statistical weight. And suppose we are taking an average of an object that is only a function of n. Yes, I mean, you could do that. We just did that. We calculated something that was only a function of px squared over 2m. And there were other variables like py and pz and x and y and z, and a wasn't a function of any of them. What I can do is say I am going to take the sum in 426 and I am going to regroup terms. And I am going to say that the sum of, or maybe I should say it, the average of a sum is the sum of an average of the averages, and therefore I can go into that triple sum, summation NLM, W sub NLM, and I am going to sort out the sum on n and the sums on L and M. And you see that in 4.27. And there's a sum on n, and a sub n is only a function of n. And then I collect all of the terms in the statistical weight, which are with the same value of n, and I add up all of the values of L and M. Okay? Mm-hmm. Well, when I do that, I have that term in square brackets in 4.27. And I can write a symbol for that term. I call it sigma n, a reduced distribution function. And the reduced distribution function is a function of n. And all of the variables that are not functions of n, I have summed over. And so I've collected the statistical weight for all of the terms in which n has one particular value and L and M do whatever they want. And that's sigma n. And having generated a reduced distribution function, that is, I can take that and I can plug it into equation 4.26, and I get the average value of A is the value of A in the state characterized by n times the total statistical weight of all of the states in which n has that particular numerical value. So I've collected things. Yes?
Mm-hmm.
Okay. And then I actually charge through and work some examples of it. And some of the examples are, we'll do an average and we'll do a reduction. And then we pull up to 4.6, the density of states, which I will talk about briefly because density of states shows up in many contexts. However, we are sort of done for the day unless you have questions.